Hello. So in this class we are going to discuss about basis sets. Now basis set is something which is integral to the computational quantum chemistry, and we have already started using basis set. Remember, we were using def to SVP during doing our Hartree-Fock calculation. So today we are going to know what this def to SVP is. So going into the basis set, remember what Hartree-Fock was. I was diagonalizing Fock matrix, and Fock matrix is nothing but an effective one electron Hamiltonian, and once you solve it you get orbitals, which is one electron wave function, and for molecules I will get molecular orbital, and epsilon is their corresponding energy. Now Hartree-Fock is nothing but LCAO-MO approximation, linear combination of atomic orbital to get molecular orbitals. So what I will do is that this psi here are my molecular orbitals, and I will express them as a linear combination of an atomic orbital. So atomic orbitals are phi I and psi in this case are linear combination, and Ci is the mixing coefficient. So if I take this case of water, I can express the water molecular orbital by a linear combination of atomic orbital of oxygen and these two hydrogen. See here, the atomic orbitals are localized on the corresponding atoms, whereas molecular orbitals are delocalized over the entire molecule. Now this recipe of solving the Hartree-Fock was given by Ruthan and Hall, and that is what it makes the one electron Hartree-Fock equations computationally accessible for molecules. And what you are going to get this problem is that what is solving a Hartree-Fock essentially leads to the finding out this combination coefficient. That is what your Hartree-Fock problem finally becomes. Now this atomic orbitals are actually acts as a basis set for forming my molecular orbital. I get these atomic orbitals from a solution of atomic Hamiltonian, and as they are the solution of an Hermitian operator, we know it is a complete set. So in principle this relation can be exact provided this L is infinite, and this L's are preset basis functions. So even before you start the Hartree-Fock calculation, you need to choose your basis set, and the moment you choose your basis set, your phi's are constant. So what you are left with is to find out this combination coefficient, that is C mu I. Now you can choose these phi's in a multiple ways. Of course, if you take it infinite, then it really does not matter what kind of atomic orbitals you are choosing, because up to the time you are obtaining by solving it some Hamiltonian, it is a complete set. So that is an exact relation. Problem is that you cannot take infinite number of basis function. So you need to truncate this series. So this relation is as best as an approximation, and when you take an approximation, then it becomes your approximation versus my approximation. So you want to choose an approximation which gives you the best possible accuracy at the least computational cost, and that is what makes the choice of a basis set an interesting topic in quantum chemistry. Now larger basis set of course gives higher quality of wave function, but they are more computationally demanding. So in this following lectures, what I am going to show you how hydrogen atomic orbitals are and how they actually lead to Slater type of orbital, and what are practically what is used is called Gaussian type of orbitals, and how the numerical basis set looks like. So this is how the lecture will be. Now remember the hydrogen atomic orbital, and this is hydrogen atomic energies. It's like it can be told as a energy for any hydrogen like atomic system, and this is how my orbital looks like. Each state is designated by 4 quantum number n, l, m and ms, whereas ms is the spin quantum number, and depending upon what is the value of n, I can have like k shell where n is equal to 1, l shell where n is equal to 2, m shell n is equal to 3. And if I take the orbital approximation for every atom, I can fill up these shells and go on the electronic configuration. Now my hydrogen atomic orbitals, we have discussed in the first week that they are actually Slater type of orbital. So this has the form where this is the pre-exponential part, this is the radial part, this is the angular part, and n is the normalization constant. And if I plot it, this is how the plot will look like. Now first thing is that the Slater type of functional has correct cusp behavior. So this actually goes at the r is equal to 0, it actually goes up because the nucleus is there, and at infinite distance you will see that this actually follows decays exponentially, and that is why at infinite distance the wave function will decay. So, it follows the correct boundary condition. Next thing is that it correctly mimics the hydrogen atomic orbital, because that is what the hydrogen atomic 1s looks like. And because it correctly mimics the hydrogen atomic orbital, in principle they would also mimic any other higher atoms up to the time you stick to the orbital approximation. So, that should have been a more natural choice for using basis set. So, Slater type of orbital should be the natural choice for the basis set functions, because it has the correct behavior for the atomic orbitals, and that is one of the reasons I am taking the atomic orbitals as my basis set. I could have taken any other set of function. Up to the time it is a complete set, does not really matter. But remember, in practice I cannot have an infinite set. So, I have to truncate, and to truncate I need some intuition out of it, and chemistry can give me that intuition. That is why I am taking atomic orbital, because I know the chemistry how linear combination of atomic orbital gives you molecular orbital, and that is why the Slater type of orbitals give me a more natural choice, because I can choose depending upon what chemistry I want to reproduce. The problem is that there is no analytic method to evaluate the Coulomb and the exchange integral over Slater type basis functions. So, calculation can be extremely slow. So, what we switch to is GTOs or Gaussian type of basis function. Now, if this is my Slater type orbital looks like, my single Gaussian will look like this, whereas if I use 3 of the Gaussian, it will look like this. In none of the case you can see that the cusp behavior is correct, because at the 0 it has a 0 slope, which is not the case in the case of Slater. So, first thing is that it does not give you a correct cusp behavior. Even at the r is equal to infinite, you can see that it is actually decaying very rapidly, whereas in Slater decays very more slowly. So, both at 0 and infinity gives you the wrong behavior. Then the question is why I am even getting bothered to use this Gaussian. Advantage with this Gaussian is that the analytic evolution of Coulomb and exchange integrals are quite straightforward using Gaussian wave function, Gaussian type of basis functions, because the product of two Gaussian primitive will lead to another third Gaussian localized on a different center. That is why calculating these integrals becomes very easy, and because of the use of Gaussian type of orbitals, the practical calculation of Hartree-Fock method has been possible. And that is how the name of one of the popular software package came as Gaussian, because it uses Gaussian type of orbitals. Now, the problem is that Gaussian is very good, but Gaussian is not Slater. It does not have the correct behavior of the molecular orbital. This is how my Slater orbital looks like, the black one. Of course, none of the Gaussians I have, GTO1, GTO2, GTO3, none of them give you the correct behavior. So, if you see that the lowest one, the GTO3, actually gives you a correct behavior at r is equal to infinity, whereas r is equal to 0 the behavior is completely wrong. Now, if you see the other one, that is GTO2, GTO1, the GTO1 actually gives a correct behavior or similar behavior at this region, but not at the r is equal to 0 or r is equal to infinity, whereas the GTO1 actually gives you a better behavior around the r is equal to 0. So, at least it does not immediately goes to 0. So, none of them are individually correct, but what I can do is that I can take the linear combination of these 3 1 in such a way that this gives as close behavior as possible to the Slater, both as r is equal to 0, here r is equal to infinity, and as well as the middle. Of course, this is an approximation, but taking 3 Gaussian is actually better than taking 1 Gaussian. Now, let us look a little bit more detail into it, and here is the form of Slater and the Gaussian type orbitals, what we have seen in the previous slide. Now, this exponential factor, this is called zeta. This is the pre-exponential, and depending upon how many of these exponential factors it happens, it comes like double zeta basis set, triple zeta basis set, quadruple zeta basis set. So, this is the term you will hear multiple times when discussing basis set, that this is a double zeta quality basis set, you need a triple zeta quality basis set. That means it will need a function which has more than functions with more than one value of zeta. If I say double, that means it should have function with 2 values of zeta. With triples, it should have 3 values of zeta. And these alphas are also called exponent. We will see what the difference are. The more larger value is the alpha, the more compact the orbital are, whereas the more, because it is exponential minus. So, more the smaller value of alpha, the orbital will be much more diffused. And depending upon this Lx, Ly and Lz, if the summation of it will give the capital L, and if the capital L is 0, then that functions were called S kind of functions. If the L is equal to 1, they are called P kind of function. L is equal to 2, they are called D type of function, similar to the nomenclature for atomic orbitals. Now, these atomic orbitals are atom centered basis set. So, these phi's are solution of respective atomic Hamiltonian. So, because they are solution of maybe 2 different Hamiltonian, let us think of water again. I can have basis set which are oxygen, which are localized on oxygen, which I got probably from the solution of oxygen atomic Hamiltonian, and I can also have orbitals which are solution of hydrogen atomic Hamiltonian. Because they are solution of 2 different Hamiltonian, I cannot say they are orthogonal. Remember, orthogonality comes due to the Hermiticity. So, Hamiltonian, the orbitals which are solution of the same Hamiltonian are orthogonal, but that may not be the case for the different solution of different Hamiltonian. So, they may not be orthogonal, but they are always normalized. So, this will follow these 2 relations in this case. Now, if I just again go back to the atomic orbitals, Slater type of orbitals or STOs. So, what these zetas are? These zetas are actually related to what is called the effective nuclear charge, Z effective. And if you see the values of Slater orbital parameters for atoms, you can still get it. So, let us think of this one. If I for a particular atom, for helium the Z effective is 1.687. Now, you see this in this case, if I go down this table, I see that my values of the exponents actually decreases, and smaller exponent means my orbitals will be much more diffused. The more I go out from 1s to 2s to 2p my orbitals will be more and more diffused. The 1s will be more tightly bound, 2s will be slightly more diffused, 3s will be more diffused, like that. And if you go from left to right to this table, you can see the value of this exponent of the Z effective is actually increasing. That essentially means that if I go from lithium to beryllium to boron to carbon, my orbitals will get shrinked. And the reason is that as I am going from left to right in a periodic table, my atomic charge is increasing. Because now my atomic charge is increasing, it will attract the electron more heavily, so that the orbitals will become more and more tight. That is what the physical picture actually means like. Now, with this knowledge, I know that I cannot calculate in terms of Slater, and Gaussian does not give you the correct behavior. So, what I will use is called contracted Gaussians. What the contracted Gaussian means? So, I will take linear combination of Gaussian type of orbitals, which are GTOs, and I will take a linear combination in such a way that they will mimic the Slater type orbitals. So, this contraction of this Gaussian, so the linear combination of these Gaussians are called CJF or contracted Gaussian functions, and whenever from now on I talk of Slater type of orbital, what I will actually mean is contracted Gaussian functions which were generated by linear combination of atomic orbital, and it is supposed to mimic the Slater type orbitals. I will not use any Slater type orbital for any practical calculations. And the product, and why these are so easy to use, because the product of Gaussian primitive is another Gaussian, and the integrals can be easily calculated, so it leads to huge computational saving. Of course, the price we pay is the loss of accuracy. And to compensate for this loss, we combine the GTOs, and by adding the several GTOs, you can get a very good approximation to the Slater type orbitals. And the more GTOs we combine, the more accurate is the result. In principle, if I have an infinite number of GTOs, that also gives me a complete set. So, that gives you an exact Slater type orbitals, but of course, for practical applications, I need to make approximation, and we have to choose these orbitals in such a way that we make a good approximation. So, therefore, it is essential to know the nomenclature, how these primitive Gaussians and the contracted Gaussians are called, then you can make an informed decision what kind of orbitals you need to take for your calculations. And the first one, of course, we have already discussed is STO-NG, that Slater type of orbital which is obtained from n number of GTOs, and they are what is called a minimal basis set. And this is what we have already seen, that I have taken 3 of the Gaussian orbital to make an STO-3G basis set. 3 of the GTOs will give me a linear combination to generate an STO kind of orbital. They are Slater type of orbital, not exactly Slater orbital, and that is what will be my minimal basis set possible. And if I have to look at the orbital, for the Slater type of orbital, this is how the orbital will look like. So, if you see, there are 2 things. There is this is an exponent, this is my zeta, and then there is a pre-exponent in this case. So, if I take the STO-1G, this is how it will look like. Now, I can take 3 of this Slater type of orbital, each with different values of the exponents. You can see the values here. The first one with a value minus 0.1689, the second one is minus 0.6239, the third one is minus 3.439. So, these are called exponential or exponents, and these are the combination coefficient, the DAIs, what you use to combine. This combination coefficient determines the what is the final shape of your contracted GTOs, and this individual of these GTOs are called GTO primitives. So, I am taking GTO primitive, I am taking linear combination, and that is going me contracted Gaussian functions which is supposed to mimic the Slater type of functions. And these are, as I told, these are called minimal basis sets. Now, of course, these minimal basis sets are not good. So, for any practical, so for minimal basis set, what happens that you have a single contracted Gaussian function for each atomic orbital up to valence electron, but that is not practical. So, you need more than one. And why you need more than one? Let us think of this molecule. Let us say I have this HCN. So, this is the central carbon, and I have an hydrogen and I have a nitrogen. Now, with the hydrogen it is doing a single bond, it is a sigma bond, but with the nitrogen it will do a pi bond. So, if I just have one Slater type of orbital here or contracted Gaussian function here, the same orbital I need to use to bond to the hydrogen and nitrogen. Now, see, the nature of the bonding is completely different. To do a pi bonding, it will have this kind of lobe where there can be an parallel overlap, whereas here the overlap has to be heads on. So, because of this it's desirable, because of this it is desirable that you have different contracted Gaussian functions with different behavior, so that it gives you flexibility to get proper geometries, get proper bonding. And that is why you need to get, of course, if single contracted Gaussian function is not good enough, then you should go to double zeta. You have more than 1, 2. But thing is that the more you increase the number of contracted Gaussian, your computational cost increases. So, here we are going to use our chemical intuition. We know that it is the valence orbital which mostly participates in bonding, and the core orbitals are generally inert. So, that means for describing chemistry, I have to describe the valence orbital in a much better way. So, there I will use 2 sets of contracted Gaussian function, whereas for core orbital I can just use 1 set of function because they are not relevant for most of the properties. And that is what is called a split valence basis set. Why split valence? Because I am splitting my valence orbital into more than contracted Gaussian functions. For example, if I go to the so called double zeta, what I will have is that I will have the each for 2s, let us say I am thinking of carbon, I will split this 2s into 2 set of Slater type orbitals. One is with the exponent 1, the other is with an exponent 2, and this is the combination coefficient. And then of course, I am going to extend all both of this Slater type of orbital into different Gaussian functions, and that is what it leads to Pople kind of basis set 321G, 631G. We are going to come what is this 321, 631 actually means. So, let us think of this nomenclature 321G. So, first thing is that when it says 321G, that means my core has one kind of Slater type orbital which is marked in red, and my valence has two kind of set type of orbital. The first one is marked in blue and the second one is marked in green. Now this number says that how many of Gaussian orbitals are used to expand the Slater type orbital. For the inner shell orbitals we have 3 Gaussian, that is why it is called 3, and for the valence orbital, the first of the Slater type orbital, I have expanded into 2 Gaussian function and the second one I have expanded into 1 Gaussian function. That is why it is called 3 to 1G. And of course, if I can have triple zeta basis set where for the valence orbital I have 3 sets of Slater type orbitals where and the inner core is described by one set of core orbitals. We are going to see an example of this one and we are going to see what is the combination coefficient and the exponent look like in these cases. So let us go to the double zeta basis set carbon 2s example. So again remember it is called 3 to 1G because the core orbital has 3 Gaussian and 1 Slater type of orbital, and the valence orbital have 2 Slater type of orbital. The first one is expanded with 2 Gaussian and the second one is expanded with only 1 Gaussian. So this is how the basis set looks like. So for the core orbital you see I have 3 S functions, 1, 2, 3, these are my exponent and this is my combination coefficient. For the valence orbital I have 2 sets of Slater, L2 and L1. The first one is expanded with 2 sets of Gaussian functions and the second one is expanded with 1 set of Gaussian functions, and these are the exponents and these are the combination coefficient. Now if you may think that okay, this is exponent of what? S type of orbital, P type of orbital. So in this case what you do is that you use a common exponent for the S and P type orbitals, and these are basically the combination coefficients. So the first one is the combination coefficient of S type of orbital and the second one is the combination coefficient of P type of orbital. Let us look into more closely. So for the first 1s, the 1s of carbon, its linear combination of 3 Gaussian, remember. So these are the exponent 1.72, 2.59 and 5.53. You can see the exponent here, and this is the combination coefficient 0.61, 0.35, 0.70 like this. Now let us go to the 2s. 2s is actually linear combination of 2 functions, 2s1 and 2s dash. So for the first one you see this is the exponent and these are the combination coefficient, one is minus, one is plus, and for the other one of course the exponent is 0.19 but the combination coefficient is 1. For the P they have the same exponent 0.364 and 0.70 but the combination coefficient is different. So by doing this I can actually do a calculation for the what are the number of Slater type of orbital and what will be the number of Gaussian type of orbital in a basis function. Let us see another example. Let us go to the example of lithium. Lithium 3 to 1G basis. Remember it is the same thing. For the core it will be 1 set of Slater and it will be expanded in 3 Gaussians. You can see it here, 3 Gaussians, and for the valence both for S and P there will be 2 set of Slater, one will be expanded with 2 Gaussians and the other one will be expanded with 1 Gaussian. And here it will show you the combination coefficients and the exponent at the same time. So you can see that here in the first case these are the exponent 36, 5.48 and 1.11, and these are the combination coefficient, and for the 2s inner this is the combination coefficient and exponent. The P has the same exponent but different combination coefficient. Problem is that if you calculate the energy value for this one, this will not give you such a good agreement with experiment. Of course, you cannot calculate the total energy from the experiment ever. What you can only get is relative energy. So what you can do in this case is that we know that lithium has 3 electrons, 1s2, 2s1. So I can calculate their corresponding ionization energy, and if I add them together, of course with the proper sign, that will give me an approximation to the total experimental energy of this one. And if you see that if I calculate it from the Hartree-Fock calculation of lithium, this does not give you very good agreement. So that means double zeta basis set is not good enough. So what you need to do is to go to triple zeta kind of basis set. So what is there in the triple zeta kind of basis set? So now Again, see the nomenclature very carefully. It is 6311G. That means my core will be again have a single slit of Slater, and my valence will be splitted into 3 Slater type orbital. The first one will be expanded with 3 Gaussian, the second 2 will be expanded with 1 Gaussian each. And you can see these are the exponent for these 3 Gaussian for the first shell, and the other 2 has a different exponent. The combination coefficients are given here both for S and P, and the core orbital now also you see that it actually has higher number of S function. So, more number of Slaters and more number of Gaussian I use, it will give me much better results. And if you calculate the energy, now you see the energy comes to 202.15, and which is in very good agreement with the corresponding experimental value. Of course, there is some disagreement, and that is due to what is missing in the Hartree-Fock, which is called a correlation effect. We will come into that. Now, let us try to do some calculation without looking into it. Can I look at the name of the basis set and can find out how many Slater and Gaussian type of orbitals are there? Now, so we will start with the example of a simple molecule methane, and we will try to find out how many Slater and how many Gaussians are